All right, Unit 3, Day 1. First day, new unit. This unit is another review unit, our last really full blown review unit. And we're going to really focus on, we focused on trig last chapter and how to graph them and different characteristics of trig curves. This chapter is going to be everything else, all the other kinds of shapes that you've learned about. And today we'll start with a couple. But a lot of the graphing techniques that we used with trig last unit, we're going to use the same ideas now. So if you got good at it with trig curves, it should help out with these curves. It'll just be that first parent function that's a little different. So we're going to make sure we're really knowledgeable about all these functions. Know them inside and out, can make quick sketches. So we'll just start with lines. Most basic curve function learned about. They have a constant slope, sort of like the defining characteristic as far as calculus is concerned. There's a standard form, which looks like this: ax plus by equals c, which generally a, b, and c are integers. Sometimes they want a to be positive. Slope-intercept, y equals mx plus b, probably your most memorable form. And point slope, y minus y1 equals m times x minus x1. Now, I'm going to recommend point slope. That's going to be our favorite form. Sometimes we'll change the slope-intercept, but usually you'll have a point and a slope. This is the easiest one to get an equation from. AP doesn't require any specific format. So this is the easy one to get full credit, do less work on free response questions. Sometimes we'll change the slope-intercept if we need to do other stuff, graph them. Slope-intercept has its benefits, but in general, it's more work. And I'd recommend if we start with slope-intercept. But let's just do a quick example. Let's say you know the slope is 2, and you know a point on the line, which this is all you need to write the equation of a line, a point and a slope, any point. Now if you do slope-intercept, you plug in 10 for the y, this is your x, this is your y. Plug 2 in for m, 4 for x, and then I guess you could find b. B equals 2. And then you can rewrite your equation in slope-intercept form, y equals 2x plus 2. I would recommend that you never do it this way. Even if you want slope-intercept, let's start with point slope. So point slope, be y minus 10 equals 2 times x minus 4. Free response question, done. That's it. So hopefully you see the value in that. Now, some of you guys are going to kind of fight me on this. I'm letting you know, I've taught this class many times. I know what it takes to be good and quick, get a good score on the AP test. Even if you don't want to, start practicing point slope. Now, if we wanted to, we could change it to slope-intercept by distributing the slope, adding 10 to both sides, and you get y equals 2x plus 2. I think it's like the same amount of work as the other way, and sometimes we just don't need to do it. So it does give you the same answer. So parallel lines, perpendicular lines. Parallel lines have equal, same slopes. They never intersect. Perpendicular slopes are negative reciprocal. So, for instance, if you had a slope of 2/3, then the parallel slope would be 2/3, and the perpendicular slope would be negative 3/2. Those are, by the way, shortcut notations for parallel and perpendicular that you guys should have seen before. And so let's start talking about, even though we're doing review, I'm going to start bringing some calculus in here and there as we get closer to officially starting next unit. But at least you'll have a little background, little experience. Let's say you have an equation. It's a cubic, right? Cubics kind of look like this. and you want to say, well, I want the equation of the tangent line at x equals 4. Now, tangent lines are parallel to the slope, and then they hit that point. So if you just had a generic curve and your point, this is a tangent line. And we've talked about tangent lines already. And that's something that kind of gets brought up in geometry with circles, but we're doing it for any kind of curve. So I want to find the equation of that line. So I need two things. I need a slope and a point. Now, the point is easy because I have an equation. I have the x value already. Just got to find the y value. So the point that we have for the line is 464. Then we got to find the slope. Now, the slope, one way to get the slope is from the derivative. Okay? And this is a polynomial function, which we also call a power function. And so it uses something called the power rule. And I brought this up already, but I'm gonna keep kind of giving it to you. If you have a function to some power and you take the derivative, that little prime symbol, they call it the prime, means derivative. You take the current exponent, put it in front, and then decrease the exponent by 1. That's it. It's power rule. I've shown it to you guys. Haven't required you use it on anything yet, really. But so in this problem right here, the derivative of f would be 3x squared. Then you say, well, I want the slope at x equals 4. This is a formula for the slopes everywhere on the curve that are actually never twice the same. So this would give you your slope. So your tangent line would be y minus 64 equals 48 x minus 4. Done. Point slope, leave it. Unless they tell you or you need some other form, just do that. Now, normal line is kind of related to tangent line. Normal line goes actually perpendicular to the curve, perpendicular to the tangent line. That's a normal line. So you actually use the same kind of idea. You say, well, you find the point the same way. The point is the same, 464, right? So y minus 64. The slope of normal line is perpendicular to the tangent line. So you find the slope of the tangent line, and then you take the negative reciprocal of it. And that's the slope of your normal line. So the work is the same. You can actually find both equations pretty quickly with the work for one of them. So something called local linearization. And it's this idea that any curve, any smooth curve, will appear linear if you zoom in enough. So if you take some curve and you're like, well, this is pretty curvy right here, and you zoom in on it, well, it still looks like a curve. You zoom in it more, you zoom in it more, you zoom in it more. Try it on your graphic calculator. It'll look like a straight line. Now, that just seems interesting, but it also, that idea allows us to sort of create some of the calculus that we're going to use that up close, it's pretty much straight line. And that kind of helps support some of the big ideas that we develop for calculus. Now, if curve is not smooth, like right here, which we call a cusp, then no, it doesn't look like a straight line if you zoom in on that corner. It's going to be a corner. But other parts of it will still look like a smooth curve. So just if it has a problem somewhere, well, then at that place, no. Or, corner, you zoom in like an opposite value graph, then no, it's not gonna have that quality, but anywhere else it will. So anyways, that's kind of an important idea that we'll be making use of later. In the back here, we'll talk about some other shapes. Parabolas are probably the next shape you guys learned about back in Algebra 1. And they're part of a family called conic sections. And we'll be talking about all of them eventually. I think we'll just be focusing on parabolas today. They're called conic sections because if you take a cone, upside down cone, And then you take another cone, right side up with its tip. They're just touching. So there's two cones. And then if you slice these different ways, you get all kinds of different shapes. So if you take a plane, which is a flat two-dimensional surface, and you slice it perpendicular to the axis of like rotation or symmetry or whatever you want to call it, the outline of this, now I'm drawing it kind of 3D, but if you look at it straight down, it's going to look like a circle. That's a conic section. If you tilt this, the circle kind of gets elongated and you get an ellipse. If you tilt it to where it's parallel to the side, you get a parabola because it keeps going. Then if you tilt it more to where it intersects both of these, you get these two different U shapes upside down, separated. It's called a hyperbola. So those are the conic sections: circle, ellipse, parabola, hyperbola. And there's some special cases, like if you hit right there, I guess a point right along the edge would be a line. But so parabola is one of those shapes. Now, in previous courses, you may have learned about parabolas in depth in like Algebra 2, pre-calc. Talk about things called the focus and the directrix, which are important characteristics of parabola. We don't care about them this year. They're not going to help you sketch the graph any better. We're not going to need them. So parabola looks kind of like this. It has an axis of symmetry. Sometimes we call it AOS. It has a vertex, which is where it changes direction. That's important. Now, if you draw a tangent line here, and then you draw another line down here, and you draw a point in here, this is the focus, and this is the directrix. And what's significant about them is that anywhere along this curve, they're equal distant if you've drawn it right. And so that's what actually defines the shape of the curve of a parabola, but we don't need them. We're not going to get into that. Okay? Now, the general form of a parabola or quadratic looks like this. So this is called the standard form, where you write it in standard form: y equals ax squared plus bx plus c. A, b, and c are numbers. But this is the general form, and this one has a square completed. And this is really useful because the h and the k end up being the vertex of the parabola. They give you the horizontal shift and the vertical shift. If there's no shift, then the vertex is at 0, 0. If you shift it to the right h and up k, well, the vertex now, instead of 0, 0, is at h comma k. The a value is the stretch factor, the scale factor. So this is it. This is a nice form to graph from. Now, back in Algebra 1, you guys probably memorized that this is how you find the location of the vertex. This formula, x equals negative b over 2a. And but we're not going to memorize that. We're going to use calculus. Calculus can determine this location actually pretty easily. At the vertex, the tangent line is always going to be horizontal flat. So you're always going to get a horizontal tangent line. And what's significant about a horizontal tangent line, it's flat, and its slope will equal 0, which means its derivative has to equal 0. It's the only place on a parabola where the derivative equals 0. So you could use that fact to locate it. So if you use this form right here and you say, all right, y prime is a power rule, 2ax to the first plus, now it's x to the first, so you multiply the b in front, get x to the 0, which is 1. And c is just a number. Derivatives measure change, so something that's not changing, just its derivative is 0. So this is the derivative, and if we set it equal to 0, because we know the slope is supposed to be 0 at the vertex, we solve it, we could say, okay, well, 2ax equals b, negative b, and then x equals negative b over 2a. Hey, what do you know? That formula from Algebra 1 comes from some calculus stuff. So I think we're usually, because we're going to encounter lots of other more complicated curves that have lots of, interesting bumps, valleys, and peaks like that. That's the way to identify it. Now, that kind of goes into this next topic where if you want to find the maximum and minimum function, like a parabola, it's going to happen at the vertex. That's the minimum. That's the lowest point. If the parabola is upside down, that's going to be the vertex is going to be the highest point, which is called the absolute maximum. Now, in calculus, we use something called the extreme value theorem. So I'm going to go ahead and start teaching you guys this. Extreme value theorem. Okay? And extreme value theorem, this is so here's the curve, which is some kind of parabola. And we have to have like a window that we're looking at. Okay, these are called endpoints. So endpoints are important for identifying the highest and lowest point. Otherwise, if there's no endpoints that goes to infinity, then there might not be a highest or lowest point because it keeps going down or up forever. So generically, let's say you have a curve that looks like that, and you're looking at just this window right here, right? These would be considered the endpoints, the edges, which might be the highest and lowest point on the whole window. Maybe, maybe not. We also want to consider the peaks as potential highest points and the valleys as potential lowest points. Now, we're not going to have a picture of it. So what you might think of is these kind of are like the vertices of like a parabola in the sense that they're where the curve turns around and has a flat slope for an instant. So f prime equals 0, f prime equals 0, f prime equals 0. We call these critical points, okay? CP for critical point, CP, okay? So the way we find it is we're not going to picture, so we take the derivative, 4x plus 8, and we set it equal to 0, and we solve, we get x equals negative 2. That's called a critical point, okay? So you want to identify all the critical points, and you want to identify the endpoints, and then we're going to decide which one's the highest or lowest or both. Now, technically, this is called a relative maximum, because it's a high point relative to what's right around it. It's not necessarily the highest, but relative to what its neighbors are, it's the higher. This is a relative min. This is a relative max. Now, if I were to ask you for this picture here, what's the highest point on the graph? You'd say this one. This was a relative max, but it wasn't the highest. This one was the highest. If I said what was the lowest point, some people might say this, but I would say this is the lowest point. This is the minimum, the absolute minimum, and this is the absolute maximum. So the absolute max or min could happen at a peak or valley, but it could also happen at the edges. So we have to always check them. Okay, so the endpoints are often given to you. We're going to see some problems where they're not. Critical points you find by setting the derivative equals 0. Then what we usually do is kind of a really simple way of figuring out what the answer is. We're going to put all these in a table and figure out, well, what are their y values? Because we don't have a picture. Let's just plug them all in order. Negative 5, negative 2, positive 5. Negative 5 would be positive 25. 50 minus 40 is 10, plus 1 is 11. So 50 minus 40 plus 1 equals 11. Plug negative 2 in. You get 8, positive 8, minus 16, plus 1 is negative 8, is negative 7. Plug 5 in, you get 50, plus 40, plus 1 equals 91. And from this table, we say, oh, well, this is the absolute max, right? This is where it happens. This is the location of it. And we've been answering absolute max min questions, and I always tell you, give me the absolute max min, which is the y value, but also tell me where it's at. This is the absolute min. So the max actually happened at the edge. The min happened at probably right in the middle at a valley kind of place. Now the way we write these answers is we say the maximum is 91. That is the maximum at x equals 5. So I want what the max is and where it happens. Like this, not as an ordered pair. The minimum is -2 at x equals, minimum is -7 at -2. Now, sometimes they ask you what is the min. Sometimes they ask you what's the x value of where the min happens. Sometimes they ask you both. This answer is safe in all those scenarios. That's why I want you to write like that. It's the best way to write the answer. It also helps you make sure you get full credit no matter what. Now, this next problem is based off this idea of trying to find the maximum or minimum of something. We call these optimization problems. Okay, so it's like a word problem based off trying to find the absolute max or min of something. We're going to optimize it, make it best or least or highest, or spend the least amount of money, make the most profit. So Mr. Bowers, our former principal several years ago, he didn't really have this plan, but I'm just giving him credit. He has $1,700 spent on fence to separate the freshmen from the other students. Because I don't know, freshmen. I don't know. They're pretty young and immature, and maybe we gotta keep them separate. I don't know. The solid pieces cost $10 a foot. The dash pieces cost $5 a foot. And find the value of x that maximizes the enclosed area for all students. So we're not going to actually try and find the area for the freshmen and everyone else. I'm not going to try and find those two separate areas. We're going to try and find the maximum area for everyone. And then I guess we'll decide how to divvy it up later. So what you need to realize is this picture is really super helpful, and you're going to want to write a lot of stuff on this picture. And if you don't have a picture, you're going to want to draw a picture that represents what's being described. So this is helpful. So the first step is you want to get an equation for what you're trying to maximize or minimize. So you got to decide, read the problem, and say, well, what's the thing that we're trying to maximize or minimize? We're trying to maximize area. So we need an equation for area. Now, sometimes variables already be on there. Sometimes they're not. You got to create variables. Now, be okay with creating multiple variables. Try and keep it, just go crazy. But the area is x, y. So that's the first step, number one. Okay, number two. We really want to get this equation in one variable because it's going to be kind of annoying if there's x's and y's in there. You guys don't know how to take derivatives of that yet. We're going to learn that several units later. So we want this equation in one variable. So that's the next challenge. Okay. All x's or all y's. Either one. I mean, one might be easier than the other. One might be nicer, less messy, less fractions. Okay. Now, usually there's some other constraint that helps you get a relationship between x and y so that you can replace one in terms of the other. So what's the other constraint? That we have a certain amount of money to spend. We have a cost limit of $1,700, and we're assuming that we're going to spend it all. Now, this is where we want to label this picture a little more. This is going to be y down here, right? This is going to be x. This is going to be, now if this is 40 and this is 70, then this is going to be 30. And this whole thing is x, right? So then this would be x minus 30. Okay? We're not building fences along the building. The building is kind of a natural boundary already. Now, I'd put all the prices next to them. It says the solid pieces cost $10 a foot. So I'd put $10 a foot there, $10 a foot over here. And the dash ones are $5 a foot. They're a little cheaper fence. $5 a foot, $5 a foot. So I find it helpful to put that next to all the sides of the fencing. Because the way you find cost of something is quantity times price. So we're going to get 10x plus 5x plus 10 times parentheses x minus 30 plus 5y. That should add up to 1,700. And be careful of these parentheses. You got it. First, that's x minus 30, and it all gets multiplied by the 10. Not just the x, but also the minus 30. So now we have a new relationship between x and y. So this is like a system of equations. So we're going to solve for x or y. It's up to you. So I'm going to go ahead and get y in terms of x. So that would be, I'm going to just rewrite this, clean it up a little bit. 1,700 equals 10x, 5x, and 10x is 25x minus 300 plus 5y. So I just combine like terms, simplified. And then I'm going to try and get y by itself. So I'm going to add 300 to both sides. All right, subtract 25x from both sides. Okay, so I'm going to get 5y equals 2,000 minus 25x. And I'm going to divide by 5. Now, if I'd solve for x and y, I could do that. I'd for sure get some fractions this time. 5 goes in 120 times, so 1,000 is 200, so that'd be 400 minus 5x. So we're trying to get one variable, and what we're going to do now is we're going to plug that back in up here to our previous equation so that now we can replace it so we all have all the same variables. X, parentheses, 400 minus 5x. So there we go. We have an equation in terms of one variable. It might be helpful for certain parts of your work to go ahead and simplify it. But sometimes it might be helpful to use the unsimplified version. So I'm going to keep both of them. Okay? So step number 3 now. So far, we haven't done any calculus. It's been geometry and algebra. But here's where the calculus comes in. We're going to find the critical points. Okay? Find the critical points, which sometimes I call CPs. So the way you do that is you want to find when the slope with this area function is 0. So you take the derivative of it, and this is why you should realize that we don't want the y's in there. Just want one variable, minus 10x, and so equals 0. And so then if you add 10x, divide by 10, you get x equals 40 is your critical point. You could get more than one critical point. The other thing we need to find on this step are the endpoints. Now, the endpoints can be challenging on these problems. A lot of times, on calculus problems, they just give them to you, like the last problem. They just gave us the endpoints. Well, that was super easy. This problem, we're trying to find the endpoints ourselves based off of like reality. What could we build as a fence? So whatever variable you got this in terms of, that's a variable you need to get in terms of here. And you got to figure out what's the smallest and biggest values x could have and still obey this problem. Okay? So first of all, the smallest x is, we can't get negative fences. So some people say, well, x could be 0. No, if x is 0, you get a negative 30 fence here. So smallest x could be is 30. Okay? Because we can't have a negative fence. What's the biggest x could be? Well, the biggest x could be, I feel like the easiest question to answer first is, well, what's the smallest y could be? Because the less you spend on y, the more you have for x. So whatever the smallest y is should produce the biggest x. And figuring out the smallest values of x and y, I think, are a lot easier. Now, these fences have to remain attached to the building. Could y be 0? And could you build all these fences would slide and be right up next to each other? Is that possible? Sure. Yeah. It seems kind of silly. You build a bunch of fences right next to each other, but you could do it. There's no negative fences. It's fine. So y equals 0. So then you can use this relationship that you just found right here. Y equals 400 minus 5x. And if you set y equals 0, you say, okay, well, 5x equals 400. And then x equals 80. So the biggest x could be is 80 because that's when y is the smallest, when y equals 0. So that's usually how I find the biggest. Those are your endpoints. That a lot of times is pretty challenging. So then what we do, For the next step number 4 is we plug in the endpoints and critical points, make a table, plug them into the area formula. Now, I like to use the factored version. I feel like it makes the work easier to do in my head. But you could use that one, or you could use the non-factored one. But I find the factored one is easier to do the calculations in my head. It also shows you what the x and y values are very clearly in your work. So we're going to go 30, 40, 80. We should go in order. If I plug 30 in here, it's going to be 30 times 400 minus 5 times 30 is 150. That's 250. So that's going to be 3 times 25 is 75. Add 2 zeros. If I do 40, 5 times 40 is 200. So it's going to be 200. It's going to be 8,000. If I do 80, now 80, remember that silly thing where all the fences are right next to each other? 400 minus 400 is 0. So no surprise, the enclosed area is 0, which makes sense. But you still got to show this work to justify your answer. This is the min. This is the max. So the same work can be used to find the opposite max or min. We were looking for maximum area. So now the way we're going to write our answer is we're going to say the maximum area is 8,000. Now there's units here, square feet, when x equals, now did they say x and y? They just asked for x, so I could just say x, but sometimes they say x and y. Now, when x equals 40 feet, and I'm going to go ahead and throw y in there just in case. That's the y value right there, 200. That's why I like that factor version. 200 feet. Now, we've been answering max-min questions like this for several chapters now, but I'm going to add something else. I want to say by extreme value theorem. So on the AP test, they make you justify your answers. Like you got to name the idea that supports it. By the extreme value theorem, that's what the work we're doing is called the extreme value theorem. But you also often have to describe how that theorem works. Well, how did that work? By checking endpoints and critical points. Okay? This is the way I want you to write these answers. If you don't write them like this, I will take off points on your test. I know it's a little wordy, but free response questions are meant to be wordy. And you're going to have to justify a lot of questions. It's not enough to know how to do it and get the right work. You got to show this work. You got to show the derivative equal to 0. You got to say, hey, here's my critical point. Here's my endpoints. You got to show this table. You got to show all this work. Then you got to write the answer. Then you got to justify with the name of the theorem and describe how that theorem works to get full credit. It's not enough to just have the right answer. You get less than half the credit if you just have the right answer, but you're missing other important things. So we're going to throw in a little bit of calculus in that sense. The idea hopefully makes sense. I wanted to go ahead and show you guys how to do one of the problems from the homework that's related to these kind of problems, but involves gravity. So if you grab your assignment for today, Unit 3, Assignment 1, we'll go and do a problem together. So let's see. On the back, the very last problem, says, according to Isaac Newton, velocity V stands for velocity equals the derivative of position S, position prime, use derivative. Okay, so S is near the Earth's surface for a ball tossed vertically upward 32 feet per second from an initial height of 48 feet. Find the max height. So there's a formula, and I'm just going to give it to you let's go ahead. We'll derive it, but I'm just letting you know that we'll probably, eventually just kind of remember it because it's a lot of work to derive it each time. So there's this thing called gravity, right? Pulls things down with a constant force near the surface of the Earth of negative 32 feet per second squared. It's negative because it's pulling things down. Okay, this is in general for all objects near the surface of the Earth. It has nothing to do with this specific problem. Now, acceleration is the derivative of velocity. So what we can do, since acceleration equals the derivative velocity, we can undo the derivative. And undoing derivatives is what integrals do. So we're going to undo it. This is not something you guys need to be able to do on your own yet, but hopefully it kind of makes sense to follow along with. Okay? That's why I'm doing it together right now. Now, that means that if we integrate negative 32 feet per second squared dt, we want to say, well, if we're undoing an integral and it undoes derivatives, you say, well, what would you take the derivative of that would give you negative 32? You say, well, negative 32t plus some constant c. Now, the way we find this unknown number, because there could always be this extra number here, because if you take derivative number, it's 0, right? So there could have been a number there. We don't know what it is. But that's where the initial velocity comes in. So if you plug 0 in to time, that c value is still there, and it equals what we call the initial velocity, v sub 0. Okay? So the velocity equation is officially negative 32t plus v naught, is a lot of times the way my professors in college would call it. I don't know. It seemed like a European or just not American way of saying v sub 0 or whatever. Okay. So then to get position, well, position is the derivative velocity. So position means we gotta undo velocity. Okay, gotta undo velocity. Gotta undo the derivative of s to get to s. Right, velocity is s prime. So we're going to integrate negative 32t plus v naught dt. Okay, so what would you take derivative that give you negative 32? Well, it'd have to have a t squared, right? Because it's power rule backwards. So when we take the derivative power, we put it in front and decrease it by 1. So that means we've got to increase it by 1 and then think, well, what would go here to give you negative 32? Negative 16. Plus, now v naught is just a number, so it's going to have something times t plus another new different kind of c. Some number that could just be there. And the way we find it often is by plugging times 0 in to the position equation, because it causes all these other things to drop out. And it equals what we call the initial position, or S naught. So our equation now for position due to gravity, vertical only, is negative 16 t squared plus v naught t plus S naught. So this is what you guys can use for these problems with gravity. Okay? It's good to kind of understand where it came from. We're gonna go over this again in detail in the future unit, so don't worry too much about it, but essentially undoing derivatives. Now, if you want to find the maximum height, that's what S is. S is position, which in this case, vertical motion is going to be the height of the object. So if you want to find the max height, that's an absolute max. That's like optimization. So what we need to do is we need to find the endpoints, which, by the way, usually it's times 0 for a ball. Now, this stuff they gave you here, balls tossed vertically upward at 32. This is v naught. That's the initial velocity. This is s naught, the initial height. Initial height, initial velocity. So our equation is st equals negative 16 t squared plus 32t plus 48. Okay? Now, time 0 is one of our endpoints. All right, we got to find endpoints. So time 0 is 1. And then the other time endpoint is going to be when the ball hits the ground. Or we call that when it time to impact. Now we're going to assume that when it hits the ground, it stops. Well, what if it bounces? What if it goes through the ground? And no, we're not going to worry about that. So how do you figure out when it hits the ground? Well, what's true about when it hits the ground? What's true about its height when it's at ground level? Its height is 0. So what we do is we take our equation and we set it equal to 0. And we solve for the time that would happen. So we factor GCF out. This one works out pretty nice. Factor other stuff, t minus 3, t plus 1. Okay, t equals 3, t equals negative 1. Now, you usually get two answers because it's a parabola. It's quadratic, it has two solutions, but we're not going to go back in time. No going back in time. Because that would be assuming that even though you threw the ball at time 0, the ball actually was already moving before it got to your hand, and it went backwards and hit the ground before you threw it. Okay, so we're only going to use positive time. So that's your endpoints, 0 times 0 and time 3. Your critical points. Now, by the way, that's time to impact right there. And the units would be seconds. So that's part B. Before I found part A, because you kind of need part B to get part A. So now we need critical points. Now, critical points are when the derivative of the thing you're trying to maximize, we're trying to maximize position S. So we want to find its critical points, its places where its graph has a 0 slope, because that's where it changes direction. So that's, by the way, the same as velocity. It's going to be negative 32t plus 32. Right? And then we're going to say equal to 0. So t equals 1. That's your critical point. So then we're going to make a table. And I guess probably should put time in. And we're putting position in. Okay, so we're going to put the endpoint 0, critical point 1. Other endpoint is 3. Plug 0 in here, you get 48, which is no surprise. That's the initial height. Plug 1 in, you get 64. And you plug 3 in, you get 91, negative 144 plus 9 times that, or 3 times this would be 96 plus 48 equals, it should equal 0, by the way, every time, because that's how we found it when position is 0. So here's your max, here's your min, okay? So now we could say the maximum height is 64 feet at time t equals 1 second, units, by extreme value theorem, is what I want you to write on these all the time now. Extreme value theorem. How does extreme value theorem work? What did you do? By checking endpoints and critical points. Okay, so that's your answer to part A with all the work you need. Part C is easy. You need velocity impact. Well, you found time impact was 1, right? No, it was 3. Plug it into your velocity equation, which we wrote up here. Negative 32 times 3 plus, I actually wrote velocity right here. 32, negative 96 plus 32 equals negative 64 feet per second are the units of velocity. Now it's negative because it's coming downwards when it hits the ground, right? So velocity has direction built in. If it's positive, it's going up. If it's negative, it's going down. When it hits the ground, it's going negative. So, anyways, that's a little gravity problem for you. Showed you guys how to do it. We'll get into this deeper in future units, but I'll have you start doing some of these now just to start get you thinking about it. Okay, do the rest of the assignment. Draw pictures on 13, 14, 15, label them, create variables if there aren't variables already, and do this kind of work without all the derivation stuff. It's more geometry in 13, 14, 15, area of rectangles and stuff like that. Okay.